Okay. So over the next 15 or so minutes, I will walk you through some of the recent developments in developing a standard for the testing of valves in hydrogen service. My focus is going to actually be on cryogenic hydrogen, but I will talk about hydrogen in general. And this is work that was done under MSS, the Manufacturers Standardization Society. As a background, I think everybody understands that there's a growing hydrogen economy. There have been challenges, especially in the cryogenic space, where temperatures go down to minus 425 or 423 Fahrenheit, minus 253 Celsius. And testing at those temperatures have been challenging. As we heard, if you were listening earlier to the panel, you heard the challenges of just getting down to temperature and maintaining that temperature and testing at that temperature. There, especially in the cryogenic domain, there were no consensus standards available, and so as a result, there was a demand or a need to try and find one that would suit, obviously the industry at large, the end users, as well as manufacturers and other participants. MSS decided to put together, under its severe service technical committee, to put together a task group that would then develop standards for hydrogen, for testing of hydrogen valves, and split it up into two domains. One cryogenic, basically down to minus 253 nominally, and non-cryogenic, meaning let's say ambient temperatures all the way up to 1200 Fahrenheit or 650 C. I'm going to spend most of my time talking about, as I said, the cryogenic case, but I will talk very briefly about the non-cryogenic. But to tell you that the cryogenic hydrogen testing procedure has just been published exactly 2 weeks ago. It came out and it was published. The gaseous hydrogen, or the non-cryogenic gaseous hydrogen testing procedure is still a work in progress and has not been released. It's still under review by the task group. I'll talk just briefly about the gaseous, the non-cryogenic side quickly. As it is currently evolving, this is subject to change, so please take this as a preliminary. It's a starting point, but basically it will resemble what you see here in terms of criteria for acceptance, acceptable leakage rates. There are going to be 3 rates, A, B, and C, 10 to the minus 5, 10 to the minus 4, and 10 to the minus 3 standard cc's per second per NPS, and that will be converted, of course, to DN and to millimeters. They're applicable, so rate A, B, and C are respectively applicable to soft-seated globe valve, gate valve, ball, and butterfly, then to soft-seated check valves and metal-seated ball and butterfly valves, and the highest rate would be applicable to metal-seated check, gate, and globe valves. So that's what's being looked at now, and it's still, as I say, a work in progress. These rates that I'm telling you are based on helium as the test medium. And if hydrogen is used, which the standard will ultimately allow, then a correction factor is being used because of the different behavior of hydrogen as a test medium. And that rate will be the 448 that you see, 0.448. So now I'm switching over to the cryogenic discussion. The cryogenic standard is called MSS SP166, again, just published. It covers a type testing and production testing segment. It also covers, under production testing, the testing of the vacuum jacket. It is applicable to isolation valves, and it is also permitted to be used for control valves. It does not cover relief valves. And temperatures go down to nominally 423 Fahrenheit or minus 253 C. The range on the high end of temperature is 50 degrees, the ambient temperature is considered 50 to 105 degrees F and 10 to 40 degrees C. The maximum pressure is as per B1634 at ambient temperature. The cryogenic service definition, self-definition within the standard, is minus 50 F or minus 101 C. So minus 101 C to minus 253 is the intended range for the cryogenic standard. There are two temperatures of testing. There's an intermediate temperature that the acronym is ICT, standing for intermediate cryogenic temperature, and an ultra-low temperature, ULT, of minus 253. So you have one temperature at liquid nitrogen temperature of minus 196 for intermediate testing, which I'll cover momentarily. And then you have the ultra-low temperature of minus 253, which is like the ultimate cryogenic temperature. One of the challenges that we had, and it has to do with economics, money economics, time economics, and just feasibility, is that these are relatively early days for cryogenic testing, and there are different schools of thought and different approaches that are being developed, have been developed around the world. We wanted this standard to become an inclusive one. We didn't want to exclude any particular technical means to do the testing as long as we deemed it to be appropriate. There were three basic methods out there. One of them is immersion. The other is a cryocooler or mechanical refrigeration, and the third one is flow-through method. I'm going to talk a little bit about all three. The standard itself covers all three of these methods. They are similar but not identical, but they're intended to bring the valve into the cryogenic conditions that it needs to be in order to do a valid leak test. And so the first method is immersion, and there are two subcategories to immersion depending on scale and size of the valve. One is the classic immersion tank method, which comes from SP 134, which is the cryogenic standard that MSS already has out for non-hydrogen valves, cryogenic valves. And that is what you see on the left-hand side of the screen. Basically, it's a tank. The valve is immersed in liquid, in the coolant, and then the test is done for leak testing. On the right-hand side, you see an immersion jacket, and that is done when the volume required of the coolant is so significant that it can't be properly managed, and so you basically enclose the valve in a jacket, and the jacket, not to be confused with a vacuum jacket, but the jacket acts as a coolant jacket and consumes far less coolant fluid for the testing. The arrangements are exactly the same in terms of thermocouple, in terms of flow measurement, in terms of other aspects of the test. It's just how you cool the valve. The second method that's covered is the cryocooler or mechanical refrigeration method. That is one in which there is a cooling device that you can see in the upper left corner of this arrangement on the left-hand sketch. And it essentially joins to the valve with copper harnesses, rather large copper harnesses. It connects to an enclosure around the valve, also typically copper or some other high conductor, and basically extracts the heat from the part until it reaches the test temperature. There are other techniques, but I won't get into them, and the standard actually doesn't talk about how to do it. It talks about what you should do and what you should achieve, but it doesn't give you the technical know-how. It's not a cookbook on how you should conduct this test. It only tells you you may use this method, you work out how you're going to apply the method. This is true of all the methods. The third method is the flow-through method, and that is one in which you're actually using the coolant, hydrogen or helium, to bring the valve down to the test temperature, and then during testing you switch over to the test fluid, and you run in a gaseous state, you run the test fluid through the valve and you conduct your testing. There are several steps to the type testing. I'm just talking about the type testing now. There's the basic valve preparation, which basically says we're starting with an established known valve design that already has its own integrity. It's built around a certain DNA. It could be B1634, it could be ISO, some other design standard, or your own standard, but you're preparing it and you're testing it to the criteria that you've done for this plain basic level of valve. You also are seeking fugitive emissions qualification as a starting point. ISO 15848-1 Class B H is the standard, the qualification that is required. There's a shell proof test. there's a seat-proof test. These are done at ambient conditions. Then there's the intermediate test that I mentioned at minus 196. And then there's the ultra low temperature, the ultimate cryogenic temperature test that's done. And then you come back to ambient and you repeat certain cycle testing to make sure that the valve can return to its normal function after having been exposed to cryogenic conditions. A little bit more in detail. So the ICT is done at minus 196, as I mentioned. The external boundary the external boundary pressure fugitive emissions test is done at 200 psi, but it uses ISO. So it's an ISO test, but it's done at a different pressure, specifically for the purposes of cryogenic testing. And this pressure was chosen because it's a typical pressure for cryogenic operation. The acceptance criteria is 50 ppm, and there's an optional low and high pressure test that's covered by an appendix. Then the ultimate or ultra low temperature test, which is at minus 253, is done at two different pressures. There's a low pressure test and a high pressure test, 80 psi and 230. They're governed by a set of allowable leak rates. They differ, and I'll show the table in a moment. And it's a unidirection. You can do it unidirectionally or bidirectionally. If it's a bidirectional valve, you have to test in each direction sequentially. There's also cycle testing, 5 open and closed cycles at full differential, then 200 cycles at 0 differential, so it's just a mechanical proof test, and then followed by 5 open closed cycle at full differential. This is, again, just to demonstrate function of the valve after the testing. This table is the acceptance criteria in terms of leak rate through leak rate. There are only two levels. There's the low pressure and the high pressure. In the development of this standard, we came up with multiple pressures, and then we realized that really in practice there are really only typically the cryogenic applications run around 195 or 190 psi. So testing at 230 was ample for the qualification requirements. What we see here are leak rates that derive pretty much directly from MSS 134. They're exactly the same, but now that's being done at a lower temperature. They apply to helium as the test gas. There is a conversion factor that applies if hydrogen is the test gas, and in this case it's a slightly different conversion rate from the one I showed earlier. It's 0.445, and that's because of the difference in fluid properties at that lower temperature. By comparison, so these rates that you see here compare exactly to MSS 134. By comparison, if you look at ISO 28921, there are similarities. It's in the same order of magnitude. For gas leakage, for classes below 900 or PN 160, they're looking at numbers like 50 to 250 as opposed to, for example, 67 and 200. So you see order of magnitude similarities. And the same is true in 5208. They run in the range of between rate CC and rate E, depending on the value. And so this again gives you an order of magnitude similarity to what the requirements are for leak rate. But again, they stand alone, and they're not intended necessarily to try to line up with these. I'm just giving this for comparison purposes in this discussion. There's a production test. There is no requirement for specific valve selection. That's by mutual agreement between the manufacturer and the purchaser. There's a basic shell and seat production test that follows MSS SP134, nothing special there. There's a fugitive emissions test that also follows 15848-2, which is the production test, but it's done at 200 psi versus 90, which is the normal pressure for the ISO test. There's a vacuum jacket test, which I will talk about a little bit more at length, with a maximum leak rate of 10 to the minus 7 Pascal meter cube per second, and a requirement for documentation and tagging. So this is just a schematic. You see on the left-hand side an illustration of a jacketed valve that's being tested. On the right-hand side, you see a schematic of the three basic volumes involved in the testing. The test investigates leakage from the vacuum jacket into the valve, or from the valve into the vacuum jacket, and from the atmosphere into the vacuum jacket in sequence. So you have two steps: the evacuated jacket and a pressurized valve, and you use a hood technique as per ASME pressure boiler and pressure vessel code, section 5, article 10, appendix 9, and you evacuate to a specified vacuum level. Excuse me. And you pressurize to 200 psi, and then you measure. And then stage 2, you evacuate the jacket. You surround the jacket either by spraying or enveloping it with the helium, and then you measure again, and the criteria is 10 to the minus 7, as I said, Pascal meter cube per second. There's a post-test requirement for visual inspection. If there's a leakage perceived, it's an abort and start over. You don't start over. You start from the point of failure, and I think I'm going to cover that point in a moment. This I won't go into in detail. We just don't have the time. But there are a number of other related standards. I provide this as a starting point. There's MSS 134. There's the gaseous hydrogen test that I just mentioned that is still in development. There's there's API 6D Annex M. There's 15848 1 and 2, and then there's 28921 2 for cryogenic valves. And then I have become aware that ISO TC 197, which is hydrogen in transportation services, is also possibly seeking a hydrogen testing procedure for cryogenic hydrogen valves, but they're really in the very early stages of determining whether or not that's a requirement, and so they're only at the evaluation stage, and I don't believe a decision has actually been made. Other than that, in terms of consensus standards that even touch on the subject of cryogenic and hydrogen, there really isn't much out there. The standards that do exist are typically regional or national in nature, or proprietary in nature. So this really becomes the first consensus, say, national and potentially international standard. So that's one of the key takeaways. It's a first time at a consensus standard. It's a comprehensive test. It covers the type test and it covers production testing. It allows for different cooling methods to accommodate the different techniques that are available. I failed to mention, I'll just mention it now, recognizing that setting up any one of these methodologies is many zeros involved. Like maybe, probably 6 to 7 figures in US dollars. So not a small investment, and an enormous amount of time and learning involved. So once you've done it, you're not going to be very incentivized to change it, and you need to know that investing in it is based upon an accepted standard. So it gives people a chance to work within a standard that they can have confidence will be around for a while, and justifies the effort and investment required. As I mentioned, there's a companion SP in development, and it's built upon existing and established standards. We learned as much as we could from what was available out there, and we tried not to reinvent the wheel, but borrow elements from other standards where we could, try to have similarity where we could. The example, of course, is ISO 15848 being used for fugitive emissions. We didn't want to start redoing that. Ultimately, the standard was published just earlier this month. There was broad involvement. It included a really large team of people involved in synthesizing this. It took us about 3 years from inception to publication, which is a pretty quick turnaround. And I would credit that the MSS process allows us to do it. It's a faster moving process than API or ISO or ASME. and there wasn't that much of an appetite to do it in other areas. MSS was interested because there was a need in the manufacturing industry, segment of the industry, to have something that they could start working with. But of course, we did include non-manufacturers. So there were other participants in that task group, subject matter experts that came with end-user experience, engineering experience, and of course, valve manufacturing experience. So it was a balance of interest composition of the task group. And that brings me to the end of my presentation. And I think I might have just squeaked, yeah, not that late. Thank you very much. Are there any questions? Any questions?
Sorry, I don't know about time, but I will ask you just one question.
Please, yeah, we have time for at least one question.
If I understood, it was 210 samples.
Yes.
Why 210 samples?
Why?
Yeah, how did you determine that number of samples?
I can't actually attest exactly why it was 210. Paul, can you remember the history of that?
No, but it's one of those things that you've got to do something, right?
Right.
It's not like you can say an exact thing, and standards will change, and if this turns out not to be adequate, or, I don't think we'd probably lower it, but,
No.
let's see.
Well, 200 actually as a benchmark is not bad when you consider comparing it to other standards like,
For the
yeah,
01 whatever, and 5848,
yeah,
close to that.
and even the API fugitive emissions tests. So it kind of is in that ballpark. It's not intended for necessarily for, you could use it for a control valve, in which case you might want to do it more, but it doesn't require it to do that. It wasn't really, it was designed primarily with, on-off valves in mind. So 200 sounded like, yeah, you're going to get a couple years of service out of that. I know, it's not a very, but what the truth of the matter is, I kept saying, let's not let perfection get in the way of progress. So we did make certain conscious compromises, but accounting for exactly why it was 200, I don't think I could find the notes that would bring me back there.
I think the essence of my question was, this is coming from a technical perspective or economic perspective, because
It was the technical need was to demonstrate that it would function operationally, open and close, 200 cycles, and that we wouldn't have, let's say, some critical failure. And we know from experience that in 200 cycles you can see failures. We know.
205 now for at least 10 years.
Yeah.
For 5848 for fugitive emissions.
Right. Yeah.
Very similar.
Yeah. So there are similarities, and that was what influenced it. We weren't going to do 10 cycles, and we weren't going to do 2,000 cycles. So we picked a number in between. We actually did look at more than just 200 or 210, but it was 5 plus 200 plus 5. Sorry if that's not particularly satisfying, but the next time around you'll be on the committee. You're going to actually help us come up with a better number, because the ink isn't dry, and we were already talking about making changes. Oh, and the last thing I should have remembered to mention is the next step will be to seek ANSI certification for the standard, which will now give it a little bit more of a grounding as far as a internationally adoptable standard. Certainly ANSI isn't intended solely as international, but it'll have, I think, a little bit more credibility as an international basis. So that's the direction we're going to take that in. Any more questions? Well, thank you very much. Thank you for your attention. Have a good show.